All right, everybody. We're gonna do a MCAT problem, a physics MCAT problem that is from a blueprint test. And as you can see, the explanation is fairly long. It even starts by saying, "Woo, this is a fairly heavy question. It might be one to skip over, mark, or and save for later." Well, I'm going to show you how we can answer this question without taking that long. And without using the method that they're using. They're using kinematics, but what we can use is conservation of energy. So let's read the question. The question states, suppose a moderately hard surface, such as the hard packed earth described in the passage, is found to decelerate a person making a feet first landing to a stop in an average of 0.09 seconds. What is the person's deceleration in terms of g, where 1g is 9.81 meters per second squared, when falling from a height of 2 meters? Okay, so for any calculation problem, what you want to start off doing is taking an inventory of the values that are given to you. So for instance, we are given time here. We are given g, of course, and we are given a height of 2 meters. Okay, now this person is jumping and landing on some type of ground, right? So we can treat this, because it's something that is falling. The person that's jumping essentially is falling down as the person hits the ground. So we can treat this as a projectile. A projectile is anything that is undergoing an acceleration strictly due to gravity. So that could be if you had a person drop, let's say, this little box from a height of h, the box will drop and land down here. Now, at the top here, the box has no kinetic energy. So I'll say that this is initial kinetic energy is 0, but it has a gravitational potential energy. Let's just say that that's a max. And as this box falls, its kinetic energy will be or rather, its potential energy will be converted into kinetic energy until we hit the bottom here, at which point your kinetic energy final is going to be at its max, and your gravitational potential energy final will be 0. So if we were to imagine the person who's jumping and reaches a height here of 2 meters and then is falling and then hits the ground over here, right? We can treat this person who's jumping as a projectile. Now, if we take the conservation of energy stuff that I drew over here on the left, if we equate the initial terms and the final terms, we would get something like this. We would get initial kinetic energy plus initial gravitational potential energy is equal to final kinetic energy plus 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 final potential energy. Now, what's the formula for kinetic energy? 1/2 mv squared plus, and we already oh well, gravitational potential energy is mgh. That's equal to, on this side, maybe I'll put a subscript for 1 for the velocity 1, but velocity 2 here squared plus, actually, I'm not going to put that put the subscripts. But yeah, we would get mv squared plus mgh. Now, since we know that initial kinetic energy is 0, we can get rid of that initial kinetic energy term. And since we know that final potential energy is 0, we can get rid of that term. So now let's just do some algebra to solve for our velocity, right? Because the question's asking for acceleration, but in order to get that, we want to get velocity. Why? Because they give us the value of time. So they give us time, we just need to find velocity to find acceleration. So okay, so here we can actually get rid of these masses on both sides also, right? So then you'll be getting GH is equal to 1/2 V squared. And now let's just solve for V. V is equal to 2 times GH, but the square root of this. Now, this is a very, very useful formula for any type of projectile problem like this, in which you have a complete conversion of potential energy into kinetic energy. So, okay, let's plug in our values for this. So I'll use green for that. This will be square root of the 2 times g, I'm just going to turn into 20. And then the height is 2 feet, so multiplied by 2. So that's square root of 40. Now, how can we find a square root of a number that isn't a perfect square? Well, let's see what it's in between, right? What squares it's in between. Because we can have radical 36, which is a 6, that's below the 40. We can have radical 49, which is the 7, which is, greater than radical 40. So our answer has to be, for radical 40, something between 6 and 7, right? It seems like it's 4 away from the 36, and it's 9 away from the 7, so I would say it's a little bit less than 6.5. I'm going to say like maybe 6.3, something like that. So we got our velocity, so meters per second. And now we just take this time, which is 0.09 seconds, and divide it. 0.09 seconds. So, okay, we could do a couple of things here. I feel like most people would feel most comfortable with using scientific notation, so let's try that. 6.3. Really, I could just write the 6 over 9 times 10 to the negative 2. I use E notation. 9e negative 2 is equal to 9 times 10 to the negative 2, which is 0.09. Okay, so now we can say, okay, what goes into each of these values? So 3 goes into 6 twice, 3 goes into 9 3 times. So this would be 2e0 over 3e neg 2. So then that would be 2/3 e. So it's when you're dividing exponents, you are subtracting them. So it's 0 minus negative 2 to give you a 4, a value of 4. So that's times 10 to the 4. Now 2/3 is 6.67, and times 10 to the 4th power would give us 1, 2, 3, 4, moving the decimal point over to the right 4 times. So it'll be 6,700. And the choices are in G. So all right, so this is actually going, I mess up the math a little bit here, but it's 0 to the negative or to the positive 2. So that'll be 0.67 times 10 to the second power, which would just be moving the decimal place over twice to the right to give us 67. Now, the choices that are given to us are in terms of G, which we know is 10. So 67 is close to 70, which is 7G, and that will be our answer here. So this is a very useful formula to use right here.